So now that we have our atomization talked about, like how we actually take our sample and turn it into atoms that we can measure, let's think about what's happening in terms of the spectroscopy, in terms of the light that we're looking at and the absorption features that we're looking, or emission features that we're looking at for atoms. When we're talking about line width, what I mean here is that if we're looking at, say, absorption versus wavelength, so a typical spectrum like you might get from a UV Vis, when we look at this for, let's compare UV Vis versus atomic absorption. In some of the samples that we've looked at, if you plot things as a function of wavelength, you see these sort of big peaks here, right? So maybe this is, a molecule in solution. And we often pick the peak here. And for Beer's law to be effective, we need the bandwidth of our light that we're measuring with to be much smaller than the width of the peak that we're looking at. So Beer's law, we want the light source bandwidth to be smaller than the line width of the peak, of the absorption peak. So the line width we would call sort of like this distance here, right? How many different wavelengths are included in this one peak? And so with a monochromator, we can select a narrow band of that and do our absorption experiment, no problem. Now, if we compare that to what absorption features look like for atomic absorption, AA, atomic absorption spectroscopy, so we're still plotting the same thing here, absorbance versus wavelength, but now our peaks look like this. They're like on this sort of scale that we have here, they're almost like straight up and down lines rather than this broad peak. And so if we want to use Beer's law, which we do, we want to measure concentration as a function of the absorbance, we need if we zoom in on this, right, this is still like a peak that looks something like this. We need a light source that has something that's really narrow compared to that. Now, monochromators can't do that. Monochromators by themselves, right? So we need to go into why, first of all, why these are so narrow in comparison to a solution, and then what we can do about trying to get a light source that provides something even narrower than these atomic absorption features. And so the reason why, so there's a few reasons why these are so narrow for atoms. Narrow line widths. One reason is that these are in the gas phase. The presence of solvent around a molecule will naturally broaden the line width because you have things interacting and it changes the relative energy levels. Whereas in the gas phase, things are mostly isolated from each other. The fact that these are atoms means no vibration and rotation. We don't have these other energy levels to worry about. And so we really do, when we looked at, say, the Jablonski diagram, if you remember, right, we had all these, extra energy levels when we were thinking about molecules that, have these vibrational modes. But right, so this is a molecule. For an atom, we don't have that, right? There's just like this and this, right? There's just the different electronic states. There's nothing else to happen in the atom. There's no vibrations or rotations. And so those two are part of what contributes to the really narrow line widths. And the final one that we're going to look at is also atoms also just have what's known as the natural line width. That's due to the lifetime of the states. And we'll look at that in the next video. How we can determine what the line width is going to be for the natural line width, and this for molecules we have these other things happening, right? The fact that they're usually not in the gas phase when we're measuring them, they have vibrations and rotations, so we're often not seeing this natural line width, but we do have a limit as to how narrow these lines can get. They're not just single wavelengths.